use of lasers in society today um, have many implications and applications, from burning and welding to dental and medical procedures. If you think you've never really been around or dealt with lasers before, just think about the last time you've turned on your CD player or DVD player or Blu-ray player, because all these discs are being read by lasers. It's important that we understand how a laser works and understand that it's not just a light, but how it's used in our everyday life. The use of lasers is a paradigm shift it will be a paradigm shift in the future, just like the iPod was for music. Medical and dental facilities both will be using lasers in everyday procedures, and it's good to understand how they work.
Albert Einstein said in 1917 that it should be possible to make rays of light of a certain frequency to be directed on an atom and make the atom release its energy in the form of light. It wasn't until 1958 that the right calculations were made by Schwann and Townes to make it possible. They both theorized and published papers about a visible laser, an invention that would use infrared and/or the visible light spectrum. However, they did not proceed with any further research at that. In 1960, Theodore Maiman invented the ruby laser, which is considered to be the first successful optical or laser light. We say considered because there is some controversy that Gordon Gould was the first. We won't go into that discussion at any length now, but it is important to know that Gould was the first person to use the word laser.
The term laser is an acronym and stands for Light Amplification by Stimulated Emission of Radiation. Thus, the laser is a device which produces and amplifies light. Since it deals with light, it operates in the world of electromagnetic radiation. There are some lasers that are not in the visible spectrum and the human eye cannot detect, such as lasers used to read both CDs and DVDs. These are mostly in the infrared region. There are also lasers that you can buy at stores used to view PowerPoints and stars in the sky, which are visible to the human eye. Laser light is different from light normally encountered in daily life. The difference is in four characteristics: brightness, monochromaticity, which is a single color, collimation, which means narrow divergence of the beam, and coherence, which means all the waves are in oscillation together.
Now let's see how a laser is constructed and how it operates. There are three components that are necessary for a laser to operate properly. The first thing you need is a medium. The second is an input of energy source. It's called the pump. And the third is an optical cavity. The lasers are classified according to the state of their medium. There are four types of, mediums that we located. There can be solid mediums, gas laser mediums, liquid lasers, and semiconductor lasers. A couple of examples of a solid medium would be the earlier ruby lasers that were first around. The gas lasers are a little bit more popular. Those would be the helium neon laser, the CO2 laser, and there is also even a water vapor that can be made to yield a laser output in an infrared form.
Laser action can only occur when a population inversion has been established in the medium. The process of stimulated emission will not produce a very efficient or even noticeable amplification of light unless this condition, called population inversion, occurs. If only 2 of several million atoms are in an excited state, the chances of stimulated emission occurring are indefinitely small. The greater the percentage of atoms in an excited state, the greater the probability of stimulated emission. In the normal state of matter, the population of electrons will be such that most of the electrons reside in the ground or lowest energy levels, leaving the upper levels somewhat depopulated. The electrons are excited to fill these upper levels to the extent that there are some atoms excited than not excited. The population is then said to be inverted.
This inversion can be established by pumping energy into the medium. This input of energy will excite the electrons from their ground state to an excited state. The electrons normally occupy the lowest available energy levels. When this is the case, the atom is said to be in its ground state. However, electrons can occupy higher energy levels. leaving some of the lower levels vacant. The electrons change from one energy level to another by the absorption or emission of energy. One of the ways in which an atom can change its energy state is through what is called a radiative transition.
There are three types of radioactive transmissions: absorption, spontaneous emission, and stimulated emission. Absorption is when an electron can absorb energy from a variety of external sources. Spontaneous emission states that the entire atomic structure tends to exist in the lowest energy state possible. An excited electron is a higher energy level, will thus attempt to de-excite itself by any of several means. Some of the energy may be converted to heat. Another means of de-excitation is the spontaneous emission of a photon. The photon is released by an atom as it is de-excited, will have a total energy exactly equal to the difference in energy between the excited and lower energy levels. This release of a photon is called spontaneous emission. Stimulated emission is when a photon released from an excited atom could, upon interacting with a second, similarly excited atom, trigger the second atom into de-exciting itself with the release of a photon. The photon released by the second atom would be identical in frequency, energy, direction, and the phase with the triggering of photon, and the triggering photon would continue on its way, unchanged. Where there was one, now there are two.
If an appropriate medium contains a great many excited atoms and de-excitation occurs only by spontaneous emission, the light output will be random and approximately equal in all directions. The process of stimulated emission, however, can cause an amplification of the number of photons traveling in a particular direction. Once the medium has been pumped with an input of energy and population inversion is obtained, laser action may begin. If no control were placed over the direction of beam propagation, photon beams would be produced in all directions. The direction can be best controlled by placing the medium in an optical cavity using two reflectors, mirrors facing each other. Now, photon beams, which are produced along the cavity, are reflected at 180 degrees at each mirror.
Once the number of photons emitted and lost and the number of photons produced by atoms raised to the excited state reach equilibrium, a laser output is produced.